Okay. So this is basically going to be using stuff that we already kind of know how to do, but we're going to I don't know. It's just with like a little twist, basically. I guess I'll say. So to kind of introduce this, we'll say so far, okay, most functions have been expressed in explicit form. Okay, explicit form. Alright, so we'll take a look at it. So explicit form would be something like this. So like explicit form and will be something like, y equals. If you see something like y equals blah, 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 or dot, 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 okay? So for example, like y equals 1 over x, right? Which we know as really like x to the negative 1, right? That is explicit form. Y equals, or like f of x equals, right? That's another like kind of explicit form there too, okay? It's y is in terms of x. One variable is in turn of only one other variable there. Okay? Some equations will be defined in implicit form. Implicit form. Okay, so again, explicit form, it was y equals, something in terms of x. And of course, it doesn't have to be y and x. It could be like y equals something in terms of t or whatever. Okay. Implicit form, though, that can be written, that's something written in the form of like this. X times y, yeah, sorry, it's x times y. I just wrote the times symbol there to make it like very, obvious, I guess. Yeah, I know. I should have just written xy maybe equals 1. But there it is. Okay. Now, how are these two equations related? Both have x and y.
They're the same.
So they both equal side their equations, right? And actually, yes, they are the same thing. They are the same relationship. And you might be like, wait a minute, there's xy equals 1 here, there's y equals 1 over x here. Well, how can we tell that these things are the same thing?
You solve for y.
If you solve this one for y, you end up with this one right here. So if I wanted to take the derivative of this, well, we're not sure how to take the derivative of this because it's x times y. We've never taken the derivative with the x and the y's mixed together. But what option do I have here? Do I have to take the derivative of this thing as it's written?
Solve for...
Yeah, we can manipulate it around using our equation kind of like rules and stuff like that. We divide both sides by x, we end up with this. And do we know how to take the derivative of y equals 1 over x or y equals x to the negative 1?
Yes.
Yeah, we can take the derivative of that. So then the derivative, and in this case we're going to be doing the derivative with respect to x. Respect to x. Okay, so the derivative of y, how do we denote that? Y prime, or we could also write it like, if it's the derivative of y with respect to x, right, we're doing with respect to x, we could also write like dy dx, right? So I'm going to write that one in this case, right? Or again, like you said, or y prime, that's fine. And that's going to equal, now, the derivative of 1 over x, right, that's not a form that we can really do right now, but we could do a quotient rule, I guess, for that. Let's do this way, though, because we can avoid that quotient rule. So what's the derivative of x to the negative 1?
negative and it says negative.
That's right, remember the power goes out front, so it's negative x, and we lower our power by 1, so negative 1 minus 1 is negative 2, which then simplifies to negative 1 over x squared. So, here we introduced the idea of implicit form, but we didn't need to worry about it because we were able to write it explicitly, right, solving it for y, and then we were able to take the derivative. So even though it's in a weird form, the x's and y's are mixed up, we were able to solve for y, take the derivative, we can still take the derivative then that way. All right, consider x squared minus 2y cubed plus 4y equals 2. And let's say we want to take the derivative of this thing. Let's say we want to take the derivative of this thing. Find its derivative with respect to x. Okay. So, can we do that? Do we know how to take this derivative? Yeah, no, right? This is implicitly defined, right? X's and Y's are mixed together here. So, what can we do then? What do we have to fall back on then? Okay, we're gonna solve for y. So get it explicit. So make it explicit, which means to really just solve for y. Not explicit like explicit lyrics, but you get the idea. Okay, so solve for y. Some of you guys are feeling like saying some explicit things after you saw your test grades, and I get it. I would be frustrated too. I didn't like seeing them either. Alright, so we'll solve for y here. Okay, so how should we go about doing that? Ideas? So subtract the x from both sides, get the x squared over to the other side. That's going to be a good start. Yeah, okay, so negative 2y cubed plus 4y equals 2 minus x squared. Then what should we do here to solve for y? Factor out a negative 2y, okay? Equals then, well, that'll be like y squared minus 2. Okay, so we're able to factor out a GCF there on the left-hand side. Okay, so now how can we get that y by, how can we get some y's by itself here then? We can't? Why can't we?
Because you can't factor y squared minus 2.
Okay, so yeah, y squared minus 2 does not factor nicely. It would factor, it would be like y minus root 2, y plus root 2, but it still wouldn't be helpful because we have all, like, I can't, if I want to get this y by itself, I would have to divide over this amount, but then I still have the x and the y's mixed together. If I want to get this y by itself, well, I would divide over the negative 2y, add over the 2, and then square root, but again, I would have x and y's mixed together. So what's the problem here? We can't solve it for explicit form, so we need some other way. We need some other way to solve this. And in fact, yeah. So this, bless you, cannot be written. Cannot be written explicitly. So, to differentiate, we must use implicit differentiation, which is very much like the differentiation we've been using before. Differentiation. Okay, so this cannot be written explicitly, so to differentiate we must use implicit differentiation, the name of our notes. Okay. All right. So So the key, and before we actually like finish off this problem here, the key to finding dy dx implicitly, with the x's and y's mixed up, is to remember the differentiation is with respect to x. Okay, so the key to finding dy dx implicitly is to remember the differentiation is happening with respect to x. Before we kind of like glossed over that, right? We said, oh, it's with respect to x. Oh, it's with respect to x. Or sometimes we had t's in there, and we take the derivative with respect to t. But never have we taken like the derivative of t, or never did we like take the derivative of one variable with respect to another variable, or at least not very obviously. We actually have been doing it, but you maybe didn't. Again, you just kind of like saw it, and you're like, oh yeah, right, of course. So anyway, it'll make more sense here once we see it. I think this will make more sense now. So the key to finding dy dx implicitly is to remember the differentiation is happening with respect to x. Okay, so what does that mean? When you differentiate x terms, then differentiate as usual. Okay, when you differentiate y terms, right, because implicit x's and y's are mixed together. When you differentiate y terms, okay, you must apply the chain rule. Oh, chain rule, that's familiar. Okay. I'll show you. Yep, we're going to do that right now. So, example, we're going to come back to this one. This is a little more complicated than where I want to start. We're going to do baby steps first. Okay, we're going to give you some baby food first, and then we'll go to the more difficult ones. Okay, so we're going to differentiate the following. Okay. Let me see here. Oops. All right, so the first thing we're going to differentiate is we want to find the derivative with respect to x of x cubed. Okay. So this thing we're trying to differentiate, all right, it's just x. It's just an x term, right? So then we differentiate as usual. So the derivative of x cubed, Austin, is going to give us, with respect to x, is going to give us what? 3x squared, right? That's normal, right? It's an x term, so when you differentiate an x term, you just differentiate it like you normally would. No problem. All right. Oh, now let's try differentiating. Let's find the derivative with respect to x of y cubed minus 5. All right. So now that we do that, what is that going to look like? So Joey, the derivative of something cubed, what does that then become when you take the derivative?
3y squared.
Yeah, 3y squared, exactly right. But we've got to use the chain rule here. So we did the derivative of something cubed is 3 times that something squared, times the derivative of what's inside, though, right?
Yeah.
The derivative of y with respect to x, we denote that as dy dx. So we're multiplied by dy dx. Kind of, yeah. So this, because it's a y. So for example, we did this before. In fact, didn't we do that right here? Didn't we technically multiply by the derivative of what was inside, right? Technically, we're using the chain rule here. It's something cubed. What's the derivative of something cubed? 3 times that something to the second times the derivative of what's inside. But what's the thing inside here? X. And what's the derivative of x with respect to x? Yeah, it's dx dx 1. So we're multiplying by 1. Here, the derivative of the thing inside is y. What's the derivative of y with respect to x? dy dx. The derivative of x with respect to x is dx dx. That's why it just simplifies to just be 1. But here it's dy dx. We're multiplying by the derivative of what's inside dy dx. Okay? So that's why we have that dy dx show up here, because we're differentiating a variable y with respect to a different variable x. Here, we're differentiating x with respect to the same variable x, and so it ends up being just our normal kind of derivative. But there we have the derivative dy dx show up. Okay? Yeah. All right, so let's try another one. All right, so for example, the derivative with respect to x of the cosine of y, or cozy. Not quite, right? Cozy is C-O-Z-Y, but you get the idea. All right. So the derivative of cosine of y. So Drew, what's the derivative of cosine? So this will be, what will I write here then? Negative sine. Negative sine what though? Negative sine of. I can't just write negative sine. I have to have negative sine of what? Y. Exactly right. Y. Is that it? The derivative of what's inside, right? What's the derivative of y with respect to x? dy dx. Yep. And if you guys don't like having to write out the dy dx there, you can also just write out y prime if you want. Same thing here. You could have just written out like a y prime instead of dy dx. I like to write the dy dx because it's like more meaningful, I think. But okay. Yes.
If we were to take the second derivative, then would it become like d prime y or
Thank you.
prime x?
So great question. Well, first of all, if we were to go and take the second derivative of this, what would I have to do?
You'd have to do a product rule.
It's a product rule. And so then, yes, then you take the derivative of the individual piece. So like, for example, the derivative of this would be d squared y over dx squared, the second derivative.
D squared. Oh yeah.
Because you're taking the derivative of the derivative, so it becomes the second derivative. All right, we'll look more at that, not today, tomorrow. I want to focus on just getting the first derivative down first, because the second derivative is a little complicated because it's all mixed up. All right. I'm going to change up the variables on us now. Let's change it up, be crazy. We're going to do derivative with respect to t. That's crazy. I know, crazy. Sine of x plus 3e to the w. What? 3 variables. There's no t. We can still do this. E to the 3 e to the w. 3e to the w. So it's sine of x plus 3e to the w, and we're taking the derivative with respect to t. Okay. All right, so derivative of sine of something, Chanda. What's the derivative of sine? Cosine. So it's going to be cosine of x times, yeah, dx. You got it, exactly right. Again, so since we're differentiating x with respect to t, x is now not our normal x, right? We still have to have that dx dt. If this were if we were taking the derivative with respect to x, then just cosine of x would be fine. Since we're differentiating with respect to the t, variable t, the derivative of x with respect to t, we just denote that dx dt. So it's cosine x times dx dt. Or again, if you'd like, you can also just write x prime if you like instead, because it's like the derivative of x. Plus, all right, now I'm going to go to, so Donovan, the derivative of 3e to the w with respect to t, what will that be? So what's the derivative of e to the anything? E to that something still, right? So it's the derivative of 3 to the w is what? 3e to the w times the derivative of what's inside, though, right? What's the derivative of w with respect to time, or how would I write that? So, when we took the derivative of x with respect to time, it ended up with dx dt. Now we're taking the derivative of w with respect to t. So what would that be? It wouldn't be dx dt, right? It would be what? dw, yeah, dw dt. dw, that's right. You guys like Arthur, right? Or you can write the w prime if you like, for short. All right, questions on that? We kind of get a feel for this. I'm going to do another one here. Yeah. Awesome.
Well, the way we denote things never matter in solving.
So I think if you want to use the primes or the dy dx's, I mean, I think you should be safe doing either of those two. You should be fine. All right, let's do another one here then, and then we'll finally do the one that we were talking about earlier. I think. Oh no, we'll do that one. Okay, a little bit. We'll do the guidelines first. Okay, let's do one more practice and then we'll go over the guidelines here. All right, we'll take the derivative with respect to a, so d-da, d-da, of a times b squared. All right, so Brittany, when I go to take the derivative of this thing, what do we get to use? Chain rule will be in it. Yep, chain rule is going to be in it. All these have had some chain rule in it, to a degree. I have a times b squared. A and b are both variables. So just taking the derivative of this as a quantity, it's a times b squared. What do we have to use? Product rule. This is a product rule. This is a product rule. We have two different variables here. This is like having xy squared. X times y squared. That is a product rule, right? It's not a number times a variable. This is a variable times a variable. This is a product rule here. So, to do a product rule, we're going to do the first thing. So that's like our first thing. That's like our second thing right there. So it's the first thing times the derivative of the second thing. So what's the derivative of b squared, Brittany? 2b or not 2b times the derivative of what's inside. What's the derivative of b with respect to a? Or how we write that? db over dA. Or again, if you like, you can just write b prime plus the second, so b squared, times the derivative of the first. What's the derivative of a with respect to a? dA over dA, which is then just 1. Yeah, so you just put 1 there. That's it. That's it. That's the derivative. Boom. Okay? Questions on that? It's a what, Anna? Ugly? Yeah. Well, we'll make it look a little bit nicer here in a second, but right now I just want to make sure we have that skill down. Okay? So questions? May I move on then? No? People still writing? Okay, I'll scoot it up then, Emma. You can go from there. All right. Guidelines for implicit differentiation. Because we basically have the skill now. We didn't quite answer our question that I was posing before about trying to find the derivative of an implicitly defined function. We're close. We've got the skills, we've got the tools, we've got the talent. We just got to put it all together now. Okay, so step 1. When you are doing implicit differentiation, you're going to differentiate both sides with respect to a variable. Well, the problem will specify. So normally x. Normally it's x. Okay. Step 2. because with implicit differentiation, you're going to have an equation, so you have a left-hand and right-hand side. You're going to differentiate both sides with respect to whatever variable you're supposed to take in the derivative with respect to. Okay. Step 2, now we're going to collect all terms involving dy dx, or y prime, or whatever you have. Collect all your derivative terms there on. And again, it doesn't matter which side, but I'm just going to specify the left side here. Okay. So collect all terms involving dy dx or y prime on the left side, and move all other terms to the right side. That don't have the dy dx. Okay. So basically, we collected all of our terms with the dy dx on one side. We collected all of our all the dy dx terms on one side, and we collected all the terms that don't have dy dx to the other side, the right-hand side. Okay. So all these terms over here on the left-hand side have dy dx with them, and so we're going to then factor dy dx, or again y prime, out of the left side.
So do you literally mean don't dy or dx or anything over that?
Right. So the typical problems we're going to be dealing with are y's and x's, and so that's why you'll always that's why I'm kind of just going with dy dx here. But generically, it could be a's and b's, could be t's and s's, whatever we might be using. But for 90% of the problems, it'll be y's and x's. Okay. And then solve for dy dx by dividing both sides by the left-hand factor. One, two, three. It's as easy as 1, 2, 3, 4. Okay, it's that easy. But let's see it in practice here, right? Because we can write all that stuff down, and maybe we kind of have an idea. Maybe you kind of have an idea of it if you have a good imagination or something like that. Maybe not. Let's take a look at the problem that we were trying to take the derivative of. So, as an example here, we've got x squared minus 2y cubed plus 4y equals 2. Okay? So, I'll just say find dy dx. Find the derivative of y with respect to x of this bad boy right there. Those are our directions. Okay, again. You may manipulate this equation ahead of time however you see fit. If you want to move stuff over to the right-hand side, move stuff over to the left-hand side, you may manipulate ahead of time as much as you see fit. Right now, I don't see any use in doing any of that, so we're just going to take the derivative straight up as we see it with respect to x. Okay? So we're just going to jump right in here, taking the derivative with respect to x. All right, we ready? Yeah, okay, we're ready. So, Jack, what's the derivative of x squared with respect to x? 2x. Great. And by the way, since we are separated here by some subtraction and addition, then I can take individual derivatives of those individual pieces. So for example, the derivative of x squared, I can just focus on that, because then the 2y cubed is separated from that by a minus. So I can just do the derivative of x squared, which is 2x. Okay, great job, Jack. All right, let's go to Caleb. So the derivative of 2y cubed, well, we have to have the minus sign there, so what's the derivative of 2y cubed with respect to x going to be? 6y squared times y prime or dy dx. I'm going to write dy dx. If you choose to write the y prime, that's up to you guys. It's probably shorter and faster, but I'm going to write the dy dx just because, I don't know. You may use y prime there if you want. Okay, great, perfect. That's exactly right. Let's go to then, oh, T-Rock's not here. No, I already got Donovan. Let's go to someone else. Someone I haven't talked to yet. Goodness. Mac, the derivative of 4y with respect to x. 4. And what's the derivative of y with respect to x? Or how would I denote that? Y prime or dy dx. One or the other. I'm going to write dy dx. Equals, and then the derivative of 2 with respect to x. Anybody? 0. Okay, so now we've taken the derivative, but we have not done what the directions are asking for. This directions have asked to find dy dx. We have taken the derivative, but do we have dy dx equals something? No. So we have to isolate those dy dx's. So that's where step 2 of our guideline comes in, right? So number 1, we did that. Check. We differentiated both sides with respect to a variable, in this case x. We want to collect all terms involving the dy dx or the y prime on the left side and move all the other terms to the right side. So I have 2 terms that have dy dx, these 2, but that 2x, what should I do with that? Subtract it to bring it over. That's right. So I still don't lose your signs either. So it's still negative 6y squared dy dx, or y prime if you like writing the y prime. It is shorter. And then plus 4 dy dx equals negative 2x. Okay, so check. We've collected all our dy dx terms to the left side, all of our non-dy dx terms to the right side, and now what should I do to this left-hand side here? Factor out a dy dx, right? Both these terms have a dy dx in common, so I'm going to factor out a dy dx. So we get negative 6y squared then plus 4 times the dy dx equals negative 2x. And we're almost done. Alright, the last thing we want to do here to get that dy dx by itself, Maya, what should be the last thing that I do here to get that dy dx by itself? What's with the dy dx that we need to get rid of? So what should I do with this quantity? Divide both sides by that quantity. Exactly right. So we're left with dy dx equals negative 2x all over negative 6y squared plus 4. There's the derivative. We found the derivative. That's it. Okay, and we could simplify, yes, we could simplify a little bit more, couldn't we? The denominator, how so, Austin? What can we do?
You can factor out a negative 2 to the denominator.
Factor out negative 2 from the denominator.
And then cancel.
And so that leaves us with the 3 y squared minus 2. Sorry, I was like brain fart there. And the negative 2's cancel, and so you're left with then just x over 3y squared minus 2.
Yeah.
So, okay, either one of these is acceptable, but that's right. Okay.
All right, awesome. We're done for today.
Okay. Would anyone like to see another one, or are we feeling okay with that? You gonna see another one? See one more? All right, we'll do one
We can
more.
look at it.
We'll do one more here. Uno más. Okay, we're going to find dy dx. Given that y cubed plus y squared minus 5y minus x squared equals negative 4. Okay, so there it is. There's our equation. X and y is all mixed up here. You can see there's really no way that we're going to be able to solve for y by itself. We would have to add the x squared over, and then factor out a y, but then we divide the y's over, and we still have x and y's all mixed up, which would then require us to use a quotient rule and stuff. So we want to take the derivative as is currently written. It's going to be much nicer to do it this way than if we try to solve this for y and then take the derivative implicitly that way, because we'll have all sorts of rough stuff going on. This is easier. Okay, this is the best way to go from here. All right, so Christian, the derivative of y cubed with respect to x, what would that become then?
3y squared.
3y squared
Times
times
dy
Yep, times dy dx, or y prime again, whichever one you want to use there. I'll use the dy dx again. Plus, and let's see here, then Josh, derivative of y squared. 2y. And then times the dy dx, right? Y prime or dy dx. Minus. Alright, well, Tyler's not here, so he can't answer for us. Let's see here, who else I haven't yet? Nate, derivative of 5y, or minus 5y, with respect to x.
5 dy dx.
Yeah, minus 5 dy dx, very good. Okay, and then derivative of minus x squared, Brandon. So the derivative of minus x squared there, with respect to x.
2x.
Yeah, so minus 2x, yep, that's it, no dx necessary, right? And then equals derivative of negative 4, anybody? 0. What's the derivative with respect to x of Brandon? Who knows?
What about Bob?
D Brandon dx. D Brandon dx. All right, Connor, next thing, what should I do next now?
Add 2x.
That's right, we want to get our collect our dy dx terms to one side, add the 2x over, and yes, that means you need to rewrite this entire mess. You can do 2 steps at once if you want to, but again, the more steps you do, the more chance there is for error. Okay, great. Let's see here. Anna, next step. What should I do here? Factor out dy dx. So that leaves me with 3y squared plus 2y minus 5 equals 2x. Okay. Good. And then Emma, final step here. Plus 2y minus 5, yeah. So we get 2x over 3y squared plus 2y minus 5. And there's our derivative. Wow. Wow. Okay? Questions on any of that?
I have a question.
Right.
Why do you prefer